Okay, so we're going to be talking about antiderivatives, but before we get into that, we've got to learn a little bit of vocabulary here. Now, I want to point out this new symbol here that we're going to start seeing, okay? This symbol is what we call an integral sign, and it signifies that you should take the antiderivative of a function. So before we talk about antiderivatives, let's go ahead and discuss derivatives in general of some functions, and then see what we get here. All right, so let's start off with the first one. The first one says, what is the derivative of x squared? Well, that's pretty simple. It's 2x. Now let's take a look at the next one. It says, what is the derivative of x squared plus 10? That is also 2x. Now, what is the derivative of x squared minus 4? Well, coincidentally, it's also 2x. So what I'm getting at here is that you need to be very careful, all right, when you're taking an antiderivative, because you don't know what the original function was that you were dealing with, and we handle that in a particular way. All right, so what we're going to do is we're going to do the reverse power rule for an antiderivative. So let me go ahead and write that out here. Give me 1 second and I'll put it on the screen. So here is the reverse power rule that I mentioned. All right, we're going to learn about this rule today when we discuss antiderivatives. All right, so what is it? Okay, it says if you take the integral of something x to the power n dx. Now the dx here is really important because this tells you the variable that you are integrating, the variable that you are taking the antiderivative of. Now it's very important to understand that this is what we call an indefinite integral, because of the fact that we don't know what function we originally had. It's indefinite. Okay, think about it this way. If you have 2x in all of these functions here, all right, when you take the antiderivative, how do we know it's x squared? How do we know if it's x squared plus 10? How do we know if it's x squared minus 4? We don't. That's what makes this indefinite. So when we take an antiderivative, it is necessary to write out what's called the constant of integration, and we consider it to be an arbitrary constant. So when we take a general antiderivative, all right, an indefinite integral, in other words, what we are doing is we are getting the family of functions that could possibly have been the original function. It may not be exact, but it's the family of functions. Okay, so that's the necessity there for the arbitrary constant c, and that's why I illustrated the x squared with various numbers attached to it and took the derivative. The derivative was all the same, but it's not entirely the same when you take the antiderivative, and the constant of integration is how we address that, the plus c, if you will, in the formula. Okay, so what we're going to do is we're going to study this rule, and it says here that you should add 1 to the exponent. So it says x to the n, we start off with that, and then we get x to the n plus 1. Okay, you add 1 to the exponent of what you had, and then you divide by the new exponent, and then you're going to tack on plus c, the arbitrary constant of integration. So let's take a look at this example. I have the integral, the antiderivative, the indefinite integral of 2x dx. This tells me one thing. This tells me that my variable that I'm integrating, that I'm taking the antiderivative of, is x. So I'm going to say 2x, it was originally to the first power. I now add 1. 1 plus 1 is 2. And now I tack on my arbitrary constant c. And so when I get this, I get something that looks like this. 2x squared over 2 plus c. Well, now that I've got that, I can reduce this and I can say, well, my answer is just x squared plus c. And when you think about it, go back to the example up here at the top where we highlighted 2x in green. All right, we know that it was going to be x squared plus or minus some particular number. And this right here actually addresses that fact, okay? That when you take the antiderivative of 2x, which was way over here, you're going to get x squared plus some constant of integration, c. So this kind of addresses the whole family of functions that could have possibly been the original function. All right, but now let's go ahead and take a look at some examples. So here is our first example. We're going to find the antiderivative, okay? So we're going to find the antiderivative, and let me write that here in the instructions. Find the antiderivative. All right, now it's not necessary all the time if you're given explicit instructions to find the antiderivative to write the integral symbol. We'll see it later on that the integral symbol is just always going to be there. But in this case, we're getting started. We're learning about antiderivatives, so it's okay. We'll leave it out for a minute, okay? So what we're going to do is we're going to take 15x squared, and I'm going to add 1 to the exponent. Remember that when you took the derivative, you always subtracted 1 and you brought the power down. In this case, instead of multiplying, we're going to divide. So we're going to divide by the new power, and 2 plus 1 happens to be 3. And so then we move on to the next term. 14x was to the first power, so we're going to add 1 again, and 1 plus 1 is 2, and we divide by 2. And then we're going to write -9, and whenever you have a constant term, you always just tack on an x, the variable, which is to the first power, and of course you could divide by 1, okay? Because it was really like x to the 0 power, which is just 1, and that gives you just that straight constant -9. So you divide by that new power, and then you tack on, of course, the constant of integration, c. So what we're going to do next is we're just going to kind of clean this up a little bit, and we're going to say, okay, well, 15 divided by 3 happens to be 5x. 2 plus 1 is 3. And then we have 14 divided by 2, which is 7. And then x to the second power, because 1 plus 1 is 2. All right. And then minus 9x, and then plus our constant of integration, c. So this right here is the general antiderivative. All right, it addresses the family of functions that could have possibly been the original function that we had taken the derivative of. Okay, so a really nice example, but let's go ahead and take a look at one that's a little bit more complex. So let's take a look here at this next one that I'm going to call number 2. So we have 4 square root of x minus 2. And what does this one look like? Okay, well, what we first need to do before we take the antiderivative is rethink the way that this one looks. Okay, so what we're going to do is we're going to write it as 4x to the 1/2 power minus 2. Now, why do we need to do this? Because I need to apply the general, the reverse power rule rather for antiderivatives. So I need to have an exponent. It's necessary that I write the exponent. Okay, so it's really nothing to it. What we're going to do is write 4x to the 1/2. Now I'm going to add 1, but I'm dealing with fractions. So what I'm going to do is I'm going to remove the 1, and I'm going to write a fractional equivalent of 1. And that is to say something with the same denominator. So I'm going to add 2 over 2. So because I was dealing with 1/2, I'm going to add 2 over 2. If it was 1/3, I would add 3 over 3. If it was 1/4, I would add 4 over 4, and so forth and so on. And now I'm going to divide by that new power, which 1/2 plus 2 over 2 is 3 over 2. And then I'm going to subtract. And if you saw from the previous example with the -9, I'm just going to tack on an x right there to the first power and divide by 1 with the -2. All right, and then of course I cannot forget about my constant of integration. Now it's just a little bit of arithmetic here when we're working with the adding and subtracting of fractions and multiplying and dividing for that matter. So what we're going to do is we're going to keep the first fraction 4, flip the second fraction, 3 over 2 becomes 2 over 3. So 4 times 2 over 3, and then it's x to the power 3 over 2, because 1/2 plus 2/2 is 3/2, minus 2x plus the constant of integration c. And when I finish cleaning that up, I get 4 times 2, which is 8 over 3, x to the 3/2, minus 2x plus c. Okay, so we've got that right there. And that is our antiderivative for that function on number 2. As always, I hope this video was helpful. So remember, like and subscribe.